and Oops, recording, good. Who are both researchers at my department for creative robotics. So personally, I see a huge potential in using augmented reality to make robotics more accessible to new user groups, as the matching of digital data on the one side and physical objects on the other side is a constant challenge in our field, as you're going to see in the presentations. But to be honest, we are really only at the very beginning, I think, of implementing AR technology. So being kind of first in the track puts me in an uncomfortable position that I don't know what exactly is going to happen next. So I'm super looking forward to that as well. But when putting together the slides, because of that, I decided to shift the scope of the presentation a little bit towards providing a more thorough overview of the field of our field of robotics. So hopefully the next 10 minutes will provide you with some inspiration on how robots could be used within virtual reality, augmented reality, and of course also animation. First, I think it's important to look a little bit at the terms. So the title of my talk refers to large-scale robotics. We could have also chosen to call it industrial robotics because these are the machines, those robotic arms that we primarily work with. We chose large scale as the scope of our work is not really limited to the typical industrial processes like you see here from the automotive industry. We use those machines also for much more creative applications, like for example here a dance performance that we did for the expo in Dubai, or for example here a musical performance at an event in Geneva. We like using those robotic arms because they are such a stable motion platform. They really greatly reduce the complexities of building a custom machine, and it still leads to programming just the movement. Just movement is still kind of a tricky term because there are still quite a few complexities in it. But of course, this is much easier than having to build something with mechanical, electrical components, maybe hydraulic systems, communication systems, and so on. But a crucial part, therefore, for realizing non-standard applications is to develop new interfaces that link that movement with basically any kind of external data. My own background is actually coming from the field of architecture. And here you can see one of our kind of preferred interfaces, the visual programming environment Grasshopper, for which I developed the robot simulation and robot programming framework, KUKA PRC, standing for parametric robot control. But an interface can also be an kind of everyday item, like for example here a mobile phone controlling these puppetry robots in real time. And within the scope of this research, of course, also an augmented reality headset like Microsoft HoloLens. But how do we even get data to a robot? You would probably expect to see something like this. I mean, this is a rebadged Eclipse IDE that is used for a collaborative robot with a quite modern software architecture. The industrial reality looks a bit different. You don't program in an IDE, but you program directly on the controller, the so-called teach pendant. I mean, maybe that video is a little bit drastic. So this is how it looks for a current generation robot with a touchscreen interface. But the concept is identical because the idea is you move a robot somewhere, you save the position, and then repeat the process until the program is complete. The nice thing about this is because you program on the object, you don't have to worry about this matching of digital and physical data because you're working in one single environment. That works well for processes like welding, one of the kind of very original robot applications, but of course also for dusting off your McLaren if you want to, something we did for a pop-up store in Zurich at some point. But it's less useful when you do something with thousands of positions. So what you're seeing now doesn't look maybe like thousands of positions, but actually this is a stop motion sequence where the robot controls 2 cameras, moves a small increment, and then takes a photo and then repeats that. Here that was done to create an 8K 3D animation for the deep space environment at the Ars Electronica. So you need to imagine a 16 by 9 meter robot reaching into the audience now, which of course we can't repeat over Zoom. That also shows nicely how an industrial robot is never just the arm, but is always part of a larger system with the controller, the tool, the teach pendant, and so on. So obviously real-time control is important for the interactive processes that we want to achieve through augmented reality, but implementing that can be trickier than maybe expected. One of the reasons for that is motion blending. So if you look here at the simulation, the robot moves through that sharp corner that you see, that 90-degree or nearly 90-degree corner here at a constant speed. It doesn't slow down. In the real world, that would necessitate basically infinite acceleration to achieve. So what the physical robot can do is either to stop at a sharp corner, or if it knows the next position, it can try to blend the movement slightly. So that of course reduces the response time of a real-time system, because the robot always has to have the following positions buffered in order to achieve a smooth movement. That works well, for example, for an application like you can see here, where you create a design and then send it to the robot to be manufactured. In this case, turning 2D strokes on a tablet into 3D cuts for the robotic arm. Another challenge happens when we want to control the time. So with the robot, we can only control the speed and the target position, but we cannot by default set the time when the robot should be a given position. Now you might say, well, if you know the speed and where it's going, you can calculate the time. That would be nice, but unfortunately those acceleration and braking curves of the robot are not known, so you can't really easily predict that just by simply dividing that. A system that can do that is the so-called real-time sensor interface, RSI. So that was initially made for sending the robot tiny offset positions every 4 milliseconds, for example, to achieve a constant pressure for a polishing process. So you have a force torque sensor that gets a certain value, and then the tool moves a little bit in order to keep that constant. Of course, instead of making tiny movements, you can also do large movements. So with that system, you can then basically create time-accurate processes, because for every 4 milliseconds, you define where the robot should be. And that data could be coming from motion capture, for example. So here, together with the Future Lab, we captured the movement of the dancer Silke Grabinger. And then in Grasshopper, we interpolated it to 250 Hertz and mapped it to a 5-robot system that duplicated the movement with the exact timing. So we have one big robot doing the large movements, and then we have 4 small robots that is each responsible for a single joint. Of course, our Windows PC was not able to stream the data deterministically, so we used an industrial PLC to send the data over an Ethercat field bus to the 5 robots, so that this would really work in a very reliable and then also safe fashion. So you see the performer and the robots are quite close to each other, which is of course tricky for everything that is basically real time. The third option is of course that you can always fake it by kind of reversing the constraints. So for example, here we don't influence the movement, but instead just send the factor of a toolpath to an external live visualization system, in that case, based on VVV, because we have, of course, the option to basically send any kind of arbitrary data between our control system, our laptop, and the robot. So for example, here then the complexity of the robot movement is omitted, because the robot just sends where it is to the visualization system, that is then in turn much easier kind of controllable than the physical aspect of the robot moving around. So to come back to augmented reality, for us, we currently see the largest potential in the areas of supervision and interaction. So where is the value in seeing where the robot will move superimposed over the actual object? Well, a part of every robot process is the matching of the virtual and physical environment, because only then can a simulation be accurate. At the very least, the robot has to know where the origin of the 3D or CAD system is located in its physical workspace. And while the robot itself doesn't care about the geometry of an attached tool, if it's I don't know here, like a sander, or if it's a drilling tool, or if it's a paintbrush or something entirely different, but it has to know a reference point on the tool. And currently, that creates a large potential for errors, because we usually do this by hand. For example, we move the robots for 3 positions on an object in order to define the position of the coordinate system, or we approach a given point from 4 different directions in order to calculate where this reference point is in relation to the flange of the robot. So we think that AR can really help making sure that the virtual and physical spaces correctly overlap. That brings us to interaction. My kind of default tool to use is Grasshopper. And Grasshopper is a very geometry-focused visual programming environment. where your code forms an acyclic directed graph. This is best for production process and mass customization, where you go from, let's say, design to fabrication. So of course you can repeat that process a few times, but fundamentally it's not cyclical. So this is less ideal for interactive processes, and also Rhino and Grasshopper, their systems don't basically run on headsets, Windows-based ARM devices or whatever. Unity, on the other hand, works very well with augmented reality headsets. And we also very like the capabilities of visual scripting to allow us to visually define state machines for user interaction in a very accessible way. However, of course, the geometry library is much more limited if you want to do complex toolpath calculations. And a headset performance, again, would be too low to do this complex toolpath calculations. For us, an enabling factor now is Rhino Compute. So this is a system provided by the developers of Rhino that can run complex Grasshopper calculations easily on an external server. So we first set up a server that runs Rhino Compute to offload the complex calculations from the headset, with a nice and easy to use REST interface. But then during testing, we realized that the headset's Wi-Fi communication was also too unreliable for an industrial machine, leading to timeout errors. So we were already using a soft real-time interface. So now to solve that, we created a custom interface that basically uses very soft real-time calculation via the web technology Signal R with the headsets, and then on the other side communicates with the robot through a stable Ethernet interface. So here's a quick try of that in augmented reality, where we virtually programmed positions and then had the physical robot repeat them, just like the teaching by demonstration that I mentioned before, but in this case done in a combined kind of digital and virtual environment. We used that software architecture also for another project where augmented reality was only used for visualization. This is the Wandering Factory. It was a mobile robotic fabrication platform. And here you can see in Unity how the platform perceives its environment with a 3D camera and then prints individualized objects that fit exactly onto the scene. The individualized path planning is again done in Grasshopper, but is then exposed to the user through our Unity visual scripting based software architecture. So we're still at the beginning of this journey, as I mentioned before, but we really see a large potential in augmented reality for large-scale robotics. And honestly, we're having a lot of fun just playing around with these exciting technologies. And yeah, so thank you very much on behalf of the entire team. I'm happy to answer any questions you might have. And I'm also already looking forward to the other presentations to see what is happening in the world of augmented reality. So thank you very much.
Thank you, Hannes, for this great presentation. Are there any questions? I already mentioned I'm not an expert in robotics, but I'm very interested in animation and this connection. So you mentioned a digital puppetry project. I think it's called Pinocchio. And I was wondering, I saw it in the Museum Ars Electronica Center. Is there also a kind of interface to interact with the robots and the puppets?
To go now a little bit deeper into the kind of background of that project, I think we set up a really nice system for it, but then the initial concept was relying on someone to properly play like an entire choreography, you know, like a small puppetry play. So we prepared it from a technological side, and then basically on the Ars Electronica side, the money ran out, so that never happened. And then the next step was to look into make it more interactive. So what you saw in the video is then what we developed with using a mobile phone, where you could basically move the robot phone around. The mobile phone with its built-in sensors would track its position in the space. And then this would have the cross that controls the puppet move around. So we're currently actually in the process together with Ars to do that a little bit, but it's one of those, let's call it, ongoing projects.
Any other questions? Johannes, I'm sure you know Bot and Dolly's piece with these canvases, and this was really a very impressive project a couple of years ago. And I was wondering, they showed us a connection between an animation software. I think they used a Maya or a similar software, and they connected it with two robotic arms. I guess so. So now you have this connection to Unity. So what are your plans to do so? So as it's a computer game, is this a possibility of thinking about this more interactivity between the robot arms and a game engine and the user?
Yeah, maybe to start with the bot and dolly thing. So fortunately, I know many of the guys from there well. I mean, it's still very unfortunate that this basically disappeared then when Google acquired it. So this is also their opinion from what I've heard. So they were very curious about that. But they basically also used this RSI interface that we're now also utilizing for some purposes. But they were very soon in creating the infrastructure to basically communicate with non-real-time capable systems, where it's important to differentiate between this industrial real-time capable, which is very deterministic and PLC level, so where you really need to keep those timings, and what you would call real-time graphics, which is of course much more relaxed. But we did a workshop with them in 2014, and they basically carried in several cards with server trays just for doing everything they wanted to do. So this was a very big infrastructure that they developed. But at the same time, I think this is now nice to see that stage that, I don't know, let's say 8 years later or something like that, or 10 years later, this is now technology that is becoming much more tangible, much more easy to use. So we had experiments by one of our researchers, by Emmanuel, who's also a co-author on that paper, who tried to create machine learning for the robot moving a hula hoop. So basically he would use tracking to move the finger, then that would track it, the robot would do it, and then he wanted to implement a learning system for that. So this is, I think, really getting there, and we're really hoping to open it up. The challenge, of course, with these things is that we're still working with physical objects that are fundamentally dangerous. So especially the real-time objects, real-time applications, you are in some cases moving a 1-ton machine with several meters per second. So there is a definitive risk. So I think this is something that for playful applications, they always need to be done in a certain environment to support that. And I think university, of course, suits itself very well for that. But it's something we always need to consider. But yeah, we're hoping really to merge those aspects of augmented reality and animation with robots more easily. I think this is something we definitely contributed to with our software in the field of architecture. And maybe this could then also be interesting to, entire new fields and introduce students to new possibilities and new qualifications.
Any questions? Let me check the chat, Discord.
I know the feeling. So robots is always a bit much, but our concept is to let it kind of, how would you call it in German? It's sickern. What was that, like filter down, and then maybe at some point, if you have an idea, then really just feel free to reach out. So we're very much used to bouncing ideas of people. We have artists sending us crazy ideas. We have robot manufacturers like KUKA. If they get very crazy ideas, we're usually the people to send it to because they don't want to touch it, but they feel like it could be fun. So we get those things. So we're always happy to discuss anything really.
Johannes, thank you so much. So if there are no questions from the audience, you're still around. So maybe in the next Q&A, as we are now continuing with a similar topic. I already saw the presenter, Milad Tusi from the University of Applied Sciences, Upper Austria, interactive media students. I think you are here. Can you share your presentation or should I share it? Milad.
Hello. Yes, please share it.
Should I share it?
Yes, please.
Yes, perfect. Yeah, Milad's presentation, and of course his co-authors, is entitled Digital Puppetry Utilizing Extended Reality Technology for Animation.
Welcome to our presentation. I'm Milad Tusi. I'm an interactive media master student at the University of... Hello everyone and welcome to our presentation. I'm Milad Tusi. I am an interactive media master student at the University of Applied Sciences Upper Austria. On behalf of my co-authors, Katja Gallhuber and Michael Lankes, I'd like to present to you our topic, digital puppetry utilizing extended reality technologies for animations. Character animation is a specialized area of the animation process, which is widely used today in the fields of film, game, advertising, education, and the metaverse. Our work presents a character animation method to work with digital puppets using immersive technologies. And I'm going to talk about some challenges that will be tackled during the completion of the prototypes and the final results, which help train beginner animators and reduce animation production costs. We have read several recent studies that have informed progress on animating objects and characters in virtual and augmented reality. Our main contribution is to explore the possibilities, challenge, and limitation of digital puppets in VR that could be beneficial for animation and games in future work. After we designed some mock-ups, we started prototyping based on our concept by using Oculus Quest 1 and 2 as a target device for tracking the full body without any additional pricey trackers. The headset is cost-effective for low-budget animation, and it is a standalone device with two 6 degrees of freedom controllers. No additional PC or console is required. Our first idea was to attach VR controllers to our shoes and track our feet and use the hand tracking options to track your hands, and finally the headset for tracking your heads. However, we failed because the controllers did not stay in the fields of view of the Oculus cameras if we attached them to our feet, so it was not a reliable solution. Then we decided to continue with our second idea and focus on bringing the long tradition of the marionette, which is called the string puppet in France, into virtual reality to investigate possible interaction design choices for digital puppets that could help build animation authoring tools for beginners in the future. The virtual low-poly scarecrow puppet and the wooden controllers are modeled and textured in Autodesk 3ds Max, and the final 3D model with the materials is imported in Unity as an FX file. The character rig itself is built in Unity, and each part of the puppet body is joined together with physics components like the character joint, fixed joint, and hinge joint. To achieve gravity, the rigid body components is also used. Following these, 5 spring joints are attached to the marionette head, hands, and knees. These are connected to wooden controllers as well to rig the strings. Afterward, the line connector script is written to render the strings in play mode by using the line renderer component. We discovered that it is more optimized than including geometry for the strings. The seesaw rotation script is written to imitate the body movement of a real-world marionette. The current position in the y-axis of the individual limbs is dependent on the degree of rotation of the control bars. By grabbing the wooden control bars and changing the rotation in the z-axis, individual arms and legs can be lifted or lowered. The project is implemented in the Unity and built for the Oculus Quest 1 and 2. To provide simple interactions such as locomotion and grabbing the wooden control bars, the XR interaction toolkit is used. After correctly setting up the Guardian system, which is responsible for defining the boundaries of the play area for the Oculus headset, the prototype can be used at any possible location where it is at least possible to fully stretch both arms. In this project, the user can navigate to the marionette in the scene by using the joystick of the left VR controller to interact with the puppet in play mode. A continuous movement was chosen as a type of locomotion since it would not be possible to create animations in which the whole puppet moves by teleporting from one position to another one. The final interaction design of the puppet is strongly based on the way how controlling marionettes in the real world work. to grab the wooden control bars of the marionette, the user can reach out for them and press the grip button of the controllers to hold them. With this design decision, the user can decide with which hand the controls for the legs or the hands should be grabbed. With a combination of changing the height and the orientation of the leg controller, a simple walk cycle can be created. By lifting or lowering the bar for the arms, the general posture of the puppet can be influenced, which makes it possible to animate the puppet in a standing, sitting, or kneeling position. By lifting both controllers, a jump can be animated. While gravity is applied to the body of the marionette, the wooden controllers are not affected by any physics, which makes it possible to easily release them and pick them up again from a different perspective. This decision aims to support the users since it is easier to look at the current posture from different angles, and it prevents tangled strings that would happen with a release puppet in the real world. In the earliest stage of designing, the puppet was rigged in 3ds Max. However, the rig was not reliable enough and the movement of the puppet did not feel natural with the bone systems in Unity. Therefore, the whole rig was built with physics components in Unity, which had a more satisfactory outcome. In other early approaches, interaction for controlling the puppet was designed in a more abstract way. By controlling the left arm and the leg with the left controller and the right arm and leg with the right controller. By mapping the activation of controller to the primary and secondary buttons of the controller, the user was not only able to control each limb individually, but also could decide when to release it again. However, pressing 4 buttons individually was not intuitive. Therefore, the implementation focus was changed to analog marionette controllers. Another design idea was to let head of the puppet follow the position and rotation of the headset. This worked very well, but led to the problem that the user could not fully release the whole puppet and control it from a different perspective. For this reason, the head was attached to the arm controller in the current implementation. During the prototyping of digital marionette in VR, we found a limitation of our prototype, which becomes visible when the distance between the grab control bars becomes too high by fully stretching both arms. Since users can move their hands without limits and do not feel the stretching of strings like for a real-world marionette, extending these limits in the current implementation leads to undesired behavior. Since we still continued working on the prototype after the submission to this conference, we could also work on this limitation by restricting the movement of the controllers to the limit of the possible movement of the ragdoll. If the user wants to extend the wooden control bars further than the limit, the control bars will not follow the hands further, and haptic feedback in terms of increasing vibration of the controllers will inform the user that the possible limit is reached. At the moment, the control rig only works for humanoid puppet, but it can be easily extended for non-humanoid puppets. Future research will lead to 2 directions. The first direction will focus on building a low-budget animation authoring system in VR for people who are still new in animating characters and cannot afford expensive software and hardware. We plan to make a training scene to guide beginners on how to animate a simple walk or run cycle in VR and record their works. Then they can play the recording keyframes and walk around the virtual training room to see the outcome from different angles. Face puppeteering can be added to the current setup by intuitively driving facial expressions with buttons on VR controllers. In the second direction, we would like to use the digital marionette in a future VR game. We are currently working on using the digital marionette in a VR game and want to investigate how the puppet's physics affects the game experience. A big inspiration for this research direction is games like QWOP, Octodad, or Goat Simulator that have challenging physically based character controls. We want to measure to what extent these challenging physics for controlling a character in a VR game contribute to the game experience. Overall, the lessons that were learned during this work may benefit animators, game designers, and researchers who also intend to bring analog puppetry into the immersive virtual environment. Thank you for your time, and we would be happy to answer some questions.
Thank you for this presentation, for this great presentation. Perfect conjunction to the topic that we already heard from Johannes. So I was wondering, you mentioned challenges and one outlook concerning facial animation. I was wondering if it's really intuitive with buttons to trigger facial animation, as facial animation is very complex. Do you have any other ideas, interfaces to connect facial animation and marionettes?
Actually, for now, because we really think about making a low budget animation, so we also limit ourselves to have these Oculus headsets, which is not cost-effective headsets at the moment. And it's also possible to easily train beginner animators to use this technique of puppetering to animate their characters. So because we don't want to use other trackers and we limit ourselves to low budget devices, not high-end devices, of course, we can, for example, use some trackers for face or for body tracking, motion capture, which are very expensive and very accurate for making animation. But yeah, at the moment, because we are limit ourselves to just controllers and the headset, for now, for face puppetering, we just work on the buttons.
My first idea was, of course, connecting it with speech, so that there is another layer that is easily possible for the animator to add. But of course, if you're thinking about a low budget, then you need the devices.
Yeah, there should be some kind of a pre-recording, animation for each buttons, and then we just trigger them whenever we want to, for example, have some voices, then Puppeteer can control them.
Yeah. Any other questions?
Hi, yes, I have one. Thanks for the presentation first. I'm curious about if you worked at any point with the actual puppeteers who know how to move actual marionettes in real life, and if you got feedback from them at any point of the development?
Actually, my co-author is also here, Katja Galhuber. Do you want to take this question?
Yes, I hope you can hear me.
Yeah.
Perfect. Yes. So actually, we try to focus on or get in a lot of information from literature. So we basically tested a lot also with other students, but we did not really test it with people who puppeteer regularly.
Okay. Yeah. Thank you.
Okay.
So maybe just from my side, a comment. So I really like the low-cost approach in a way from our project, because that was one, as I mentioned to Jürgen before, we didn't have time to make a proper choreography because we didn't have enough. The big OptiTrack system was set up in a huge warehouse and we were there allowed only for a couple of days. Now we have our own, but at that time, this would have really been a super enabling factor to allow our puppeteer player to record this and then apply it to the robots. So also from my side, I don't know, I don't think this is what you're going for, to have this physically accurate, but just from my personal perspective, of course, it would be really fun to at some point say, this is how it's simulated, and then we have the robot do exactly the same what we did with the movement and then apply it. So if you want to drop by in Linz, always welcome to discuss that. And just maybe to wrap up with the puppeteers. So our experience was the puppeteers are super hard to find. We got ours through some very personal connections of mine, or through my wife actually. And that was a older guy who chiseled the entire doll out of wood by hand, and then found it funny to include a small penis in it. I don't know, Jürgen, if you noticed it. So they are a very particular crowd of people. So maybe that was better for now. I don't know, but really nice project.
Yeah.
Thank you.
Thank you.
There was no question,
Yeah,
it was just a boring comment, sorry.
No, it's very good. I got very great feedback always when talking about this project with people. And actually, I have like more than 7 years experience working with different international animation companies as a senior 3D artist, and always I have this problem with beginner animator, and even some people, they just want to get familiar with this animator task, and I always explain for them, if you want to do these tasks, you should put a lot of time and effort for that. And in this way, we can also have some our group target, for example, our teenagers who wants to get familiar with how the animation process works, and we can explain for them, just recording very easily with puppeteering some stuff, and record your works and see how you can animate a character in a virtual environment. And also then when we tested with adult, and also we got very great feedback. Sometimes we use this bounciness for strings, and we see that it's going to be very fun for them and also challenging for a game. So that's why we have also the second direction for game in our project. And it's also part of my master thesis project for interactive media, which I'm currently also working on it.
Great. So we are looking forward to your next prototype. That's
Thank you.
maybe a topic you will present next year. So any further questions, comments?
Maybe just an idea for driving facial expressions. There is software, especially for game engines, that is driving mouth expressions through speech. So they just recognize typical patterns like an E, A, O, and I, and map the correct mouth movement. Of course, you have to tell them what is the appropriate picture layer for each and every mouth movement. But maybe that's an idea to drive a simple conversation, or have facial expressions just by talking into the microphone that is built in the Oculus Quest. Just
yes, exactly.
And again, just an idea.
Yeah, very good feedback. Thank you.
Yeah, thank you for the questions and the discussion. If there are no further questions, I would like to continue with the next presentation. I'm wondering if Mike Wang from City University of Hong Kong is with us. I have not seen him yet. But in this case, we will start the presentation. Now we are going in a different direction, computer graphics. It's a 14-minute presentation, and we are hoping to see the presenter in 15 minutes. So I will share my screen again. Sorry, my fault. And now we start the presentation again.
Hi, hello. My name is Mike Wang. First of all, I would like to welcome all of you to my presentation. Today, I'm going to share with you some of my work in progress, which is about how we may take advantage of binocular vision in order to do image enhancement for virtual reality content. And here's my presentation. I hope you will enjoy it. Thank you. Our short paper is titled View-Dependent Asymmetric Detail Enhancement for 360-degree Stereoscopic VR Content. Back in 2019, I purchased my very first Oculus VR headset. And obviously it's because of this clever feature of fast head tracking. So I quickly went out to shoot a lot of 360-degree stereo pair to experience it over using this Oculus headset. And it was really quite an amazing experience to me personally. So, but that is one thing that I become quickly aware, which is after we shot any 360 image pair, on our PC desktop, they look quite, big, right? Because they cover like 360 degree. However, once we loaded them to the VR headset, the view angle, or say the proportional amount of image that can be seen through the VR headset is often limited for obvious reason. However, to me, this becomes a small inspiration, because then I'm thinking, for VR, whenever we try to look at some stereo image, it looks like that. The processing can be view dependent. And at the same time, I was doing some research about image detail enhancement. So I quickly think about how I might couple, these two ideas together to do some small research. And of course, at the same time, this is a very important consideration in my this small research, which is the binocular vision. Because we know that when we are wearing a head-mount display, the image channel being fed to our left eye and to our right eye, they are actually independent from each other. And so I was thinking whether this could be another dimension that I should explore for this small project. So basically, I'm combining three things here. First of all, I would like to take advantage of this view dependence of this VR headset image viewing experience. And then also, I would like to do some image detail enhancement for this experience. And at the same time, I would like to take advantage of the characteristic of binocular vision. So nowadays, I think the view dependence is, well, I think most, for example, the software library provided by Oculus, they work really well because through the code, it is very easy to get the current viewing angle of the user's HMD quickly. And then so, for the rest of this presentation, now I'm going to share more about the detail enhancement and the binocular vision. So what is image detail enhancement? To me, this particular project, what I am interested is about enhancing local image contrast. So on the left-hand side, it is the original image. So what I would like to do is how we could enhance those local contrasts to make the image, more interesting or more visually pleasing in terms of clarity. So basically, how we can achieve it is we can use some filter to achieve something we call image decomposition. So on the far left-hand side, which is the original image, and then after we apply the decomposition, we will be able to obtain this so-called the base image, which is in the middle of the screen, and then the image detail on the right-hand side. So once these two components are separated, then we can do some manipulation on them. So a straightforward manipulation would be the following. So we keep the base image untouched. However, now we will apply some amplification of the image, just like the middle image shown on the screen, that with the image aggressively enhanced. So by combining them, these two components together, we get an image which look like have a local contrast heavily enhanced. So basically, the filter we use is called a sub-window variance filter, which is the filter that we published last year for doing image processing. And due to the limitation of time, I invite those who are interested in this filter to refer to the original paper listed in our reference. So here I would like to show you some image enhancement result. So there's a pair of cat images. On the top, which is the original one, and then on the bottom is the one that we have the local contrast enhanced. So obviously, if you look at those whisk, the contrast is heavily boosted. Apart from that, we can also do something we call the image detail suppression. So on the right-hand side, on the top, which is the original image, so after the decomposition, and in this case, we chose to decompose into two different levels of details further. And then by suppressing, for example, only the medium detail, then we'll be able to get something like at the bottom, you know, kind of some, we applied some kind of so-called vanity effect. So now, we will look at how binocular vision plays in this small research. So basically what I would like to do is, because of the binocular vision characteristic, I was thinking, how about we try out to only enhance one image channel, which means I would like to see what would happen if people, would respond about this kind of image pair. So this first example, this image pair, we introduced detail enhancement only to the right eye, which corresponds to the bottom part of this image pair. And then we invited a group of 10 individuals to look at this image pair. But at the same time, we also let them see the original untouched image pair and also a fully enhanced image pair, which means both left and right eyes images are enhanced. And then of course, the asymmetric version too. And interestingly, here is the evaluation result. And we are quite surprised that asymmetric image that people actually also score them pretty high, even when they have experienced that fully enhanced image pair. Here is a very interesting result, which implies that this kind of image enhancement introduced in an asymmetric fashion might have some interesting potential. So we also prepared a second image pair set, which is the one that's being shown on screen. But in this case, only the left eye image is enhanced, and then the right eye is untouched. So we just to just to make sure that every viewer joining the experiment will not be able to say if anyone got maybe a stronger vision on either eye. So here's the evaluation result. In this case, the asymmetric case doesn't really, stand out a lot. However, they still match pretty close to the result of a fully enhanced image pair. And this is quite interesting. But however, we are very, very aware that this is only a work in progress. And this early result can only be used as an indicator or say, it looked like this could be a feasible direction of research. So we are planning to carry out more, in-depth and well-prepared viewing experience in the future. So here I have prepared video demo, which is captured from the Oculus headset. So basically, we wrote a very simple software which will load the image into Oculus. Right. And the image pair has a dimension of around 4K. So the viewer will, look at the image, of course, in stereo. But here I would like to invite everyone to pay attention to the image detail on the ground, for example. Now, at this viewing angle, the local detail enhancement is modest. However, when we pan to the left, you might notice that the contrast is now very, very high. Right? Especially if you look at those fallen leaves on the ground. And now we are going to pan to the right again, and it goes softer. Here we are going to pan to the far right again, and the contrast is going to increase aggressively again. And you might also notice that because the program simply increased the amount of the image enhancement channel depending on the viewing angle. So the overall performance is pretty good. So before we conclude this presentation, I have some extra insight to share. I know this is not like a big discovery. However, we noticed that by using this kind of asymmetric detail enhancement, because the high frequency information only exists or say enhanced on one image channel. So in terms of storage, we got some little savings. So the table in front of us showing the storage requirement of say the original image pair around 15 megabyte, the asymmetric run 65, and the fully enhanced pair, which means both left and right sides are enhanced, is around 18 megabyte. So I think what we will be doing in the future, one is we would like to introduce an environment which will allow the user to author the degree of enhancement in a VR setting, which means this introduces another potential which will allow, say, an artist to offer the image viewing enhancement, which is dependent on the viewing angle. However, I know that as probably many dimensions are possible for research, and I would love to hear from you too. So I know the committee will be forwarding your questions through email to me, and I would like to, have your feedback too. So I think this concludes my today's presentation, and I hope you enjoy the rest of the workshop and the IEEE VR. Thank you for coming.
Thank you so much for this presentation, but I think Mike Wang is not with us. And as he mentioned at the end of his presentation, if you have any questions, please write them into the Discord channel, and we will pass it to Mike Wang, and then we will let you know in the channel, of course, the answers. It's from my perspective, a very interesting research on asymmetrical detail enhancement, thinking about binocle rivalry in VR is quite an interesting approach. Also, artistic approaches, as there has already been some experiments by Salvador Dali with different images with different colors for the left and the right eye. And I think this is a very, very interesting approach for the future. So once again, if you have any questions, please write them into the channel, and we will try to get the answers as soon as possible and to leave it in the channel, Discord channel as well. So we will continue with our last presentation in this session. The presenter is Nils Gallis, also from the University of Applied Sciences, Upper Austria, and he will talk about a paper entitled Behind the Curtains, with a comparison of Mozilla Hub and MS Teams. And Nils, stage is yours. Can you share the presentation?
Yes, I can. Yes, I can. Hello, welcome and greetings from Austria. First and foremost, thank you for showing interest in the paper Behind the Curtains, comparing Mozilla Hubs with Microsoft Teams in a guided virtual theater experience. This paper examines the perceived social presence experienced in social virtual environment in a theater context, compared to video-based meeting platforms. But what does that actually mean? To start from the top, what was the initial influence for researching a topic as specific as this? Well, a global pandemic that captivated the world from, roughly speaking, March 2020 until today has forced sectors that are often viewed as more reluctant to adopt to the digital age to embrace new forms of technology, as they can no longer rely on physical presence of workers and audience. Facilities of cultures, such as museums, theaters, and operas, just to name a few, were promptly facing the issue of having to close the gate for visitors and therefore missing out on a significant stream of income. Schools and other institutes of education had to follow afoot, causing students and scholars to be opposed to an array of problems that inevitably come along with being homeschooled. Additionally, in having to overcome the same situation, these two sectors stand in front of another common problem: how to migrate their way of doing that has stood its ground for centuries into the digital world. Furthermore, how to make content that is engaging for the audience and conveys the same amount of informations and emotions and vibe. How did the majority combat this problem? Video meetings embedded in graphical user interfaces are the most common workaround for addressing this problem. Such meetings frequently take place in applications such as Zoom, Microsoft Teams, or Jitsi, and other channels where a webcam feed represents every participant that is visible to every other participant of the meeting. The placement and arrangement of these rectangles often vary arbitrarily and cannot be chosen or moved by the user, and are therefore restricting participants of the meeting to an extent that some might see as bothering. This circumstance may not pose a problem in work environments. Still, in education, in particular in education of younger students, where social and physical interaction is a sizable factor of a child's social development, for instance, this factor does weigh in heavily. Forcing children all over the world to sit in their homes in front of a computer looking at the same screen for hours on end might be a necessary step to bridge the time until normality can re-enter the daily life of all, but it's not the optimal solution. Social virtual reality is one way to combat this issue. In theory, it seeks to immerse the user more than by using a website or an online meeting call. A virtual environment enables the user to communicate with each other in digital space, oftentimes as a representation of oneself in form of an avatar. The aspect of communication does weigh in heavy into the benefits of social virtual environment. However, we should not overlook other aspects, such as its use in gamification of education, which is a very different topic on its own. And this is where the connection to video games can be made. Social interaction in video games have been widely discussed, researched, developed, and systems refined over the year. Social interaction in video games are an established way to communicate and create social bonds without the needs of both parties to physically be there in presence. Now that we have briefly covered the problems and the possibilities of the subject, we can ask ourselves the question, where does the added value of social virtual reality in education lie? Does it matter if a young student is sitting in front of Microsoft Teams or is able to interact more freely in a social virtual environment? How does the perceived value of one change when contrasted between visiting a certain place in virtual reality or in real life? Our paper also draws connections to other studies that were already trying to address this situation from a similar point of view. And these papers concluded that the social presence in VR is very similar to the physical presence. This outcome has been backed by numerous other research and gave us a solid foundation on what to look out for in our research. To answer our question, we teamed up with the local city theater, the Landestheater Linz, to identify and compare the strong suits and weak spots of using social virtual environment as compared to video-based meetings. The theater has planned to provide students with a more in-depth look of one of its stages and how the theater play comes together. COVID restrictions made the physical presence of these students impossible. So, we created a virtual environment, a digital rebuild of the theater stage. Based on architectural plans and pictures, we constructed the stage in a resolution that allowed hassle-free setup in our tool of choice. In the end, the students could explore the stage in a social virtual environment that you see here. This is Mozilla Hubs. But why use Mozilla Hubs? Well, the system requirements called for an application that does not need to be installed, is accessible from almost any device and free of charge to have the lowest barrier of entry possible. Additionally, this application features a variety of communication possibilities via speech, text, video, as well as expressing through gestures, and can also be entered by almost any device, be it smartphone, notebook, PC, or virtual reality headset. It is also possible to place 2D images or videos and 3D items into the space. The latter feature was used extensively over the course of this research. Because the task was as follows. The students were separated in 3 groups of various sizes. The separation was purely for the reason that people overseeing this project could focus on similar group sizes. No additional parameter was used for the separation. These 3 groups were read a piece of Johann von Goethe's Faust. Without them knowing it is the text from the specific piece of literature. They were then asked to rebuild the environment purely based on what they just heard. However, not all participants were in Mozilla Hubs. Some were joining a Microsoft Teams call and were watching the shared screen from one of the guides that was overseeing this project. At the end of all this, the students were asked to fill out a questionnaire. When formulating these questions, it was important to distinguish between participants who were able to actively participate and the ones who could not, due to various reasons. And at the same time, through various questions, we could divide between students of different age and sex, technology savvy or not, experienced with computer games or not. Over the course of several weeks, 36 students filled out the form and gave feedback on their experience in Mozilla Hubs. The results leave room for discussion. Mean values of each dimension indicate that there is no clear preference on whether the student was actively participating or watching the activity on a shared screen in Microsoft Teams meeting. There are multiple possible approaches to interpreting these numbers. However, none of them seemed to have made a clear case for one or the other option. This was a rather surprising outcome and does open the floor for a couple of more question and discussion topics. First and foremost, why? As the numbers do not deliver a satisfying answer to the question, it was necessary to conclude from all the given data, including the feedback that was given by the students at the end of the questionnaire. An assortment of reasons could be drawn. Firstly, there was a particular frustration over the control scheme of the mobile version. Being overly focused on figuring out the basics to fulfill the tasks will impede the experience substantially. There was media present which prepared students on how to interact with the system. However, this tutorial was focused on PC and notebook devices, not mobile. Another unexpected aspect of this study was presented when talking to the guides. The experience was built with the intention of increasing the possibilities for the students to interact with each other. Communication would seem to be a key component in a group task where the goal is to achieve a unified goal, yet the guides report a total lack thereof. The students rarely use the built-in chat function, nor verbally or by text. If communication was happening, it was mainly looking for confirmation if the task was understood correctly and a general search of affirmation of the taken action. This behavior stands true to the active participants and the passive participants watching the shared screen of the guide on a Microsoft Teams meeting. This result does appear to create more questions than it answered, and further research is needed. Even with the acquired knowledge of this study, is the topic of social virtual environment in art, culture, and education still worth exploring? The feedback section showed a deeper appreciation of the change of scenery. Students were excited to see this sort of diversity in their day. Taking in consideration that extensive remote learning or working can be a reality in the future, as the past 2 years have shown us, there is the wish and need to find a viable alternative to video meetings. Maybe not to replace them, but to coexist and bring diversity, maybe. Thank you.
Thank you, Niels, for your great presentation. Are there any questions? See in the chat. Niels, I'll start with the first question. Mozilla Hubs was quite popular at the beginning of the pandemic. So what is your vision of the future of Mozilla Hub? Is it still an experiment for social virtual VR? Do you see an improvement and potential for the future?
There is definitely potential. So Mozilla Hubs was maybe a step ahead of its time. Due to its simplicity, of course, it was very limited in what it could do, but opened up gates for other events because it was so simple to get into. You can just enter it on your mobile phone or on your computer or anything. It was very accessible for basically everyone, and we used it in a couple more projects where the demographic was not younger children but elderly people and people of middle age and everything, and most of those people did not have any problems with Mozilla Hubs. However, if we see Mozilla Hubs as just one example of a bigger group, which we now would call a metaverse, which it definitely can be, and if we have other examples like Facebook Horizons or VR chat, those are gaining popularity since last year massively. So Mozilla Hubs, well, I would say specifically Mozilla Hubs does not really feel substantial enough to have a longer lasting future, with Mozilla cutting down the development team behind Mozilla Hubs itself. However, the system that it represents, the metaverse and all those social virtual environments, are gaining more and more tractions, even with VR glasses being more and more accessible due to Facebook releasing Oculus Quests or China growing their market in virtual reality and popularizing virtual reality in general. So I don't see that sector being lost within the next couple of years.
Mm-hmm. So there are no questions in the chat. Is the prototype still in use? And how is the feedback from a theater?
The prototype is still in use. Now it's not used for guiding students, but for the people building the stages themselves, or the stage designers for theater plays are actually using this 3D replica of the stage to get an idea on how the stage looked like and how they can position the lighting or the stage props. before actually arriving on the stage in Linz, and maybe save them some time to have a conceptual idea before even being on place. And there were even some instances where they fully realized their idea or fact checked their idea in the digital world, and then just had a very well, it facilitated the whole process of stage designing for people who have to actually be flown in to stage design, who usually would have been flown into stage design in physicality.
Mm-hmm.
However, social virtual environments, after finishing this paper like a couple of months ago, a year ago, there were some other projects that I was participant of, mostly in the theater space and in the festival space, and people were much more happy to use the communication system. So the problem that I mentioned in the video with the students not really communicating with each other might be a student thing. As we talked to these to the guides, most of them said that they felt like there was communication going on, although not through the official channels, but maybe through a Discord server that was running in the background, or for TeamSpeak or something. However, they didn't see any communication through the official channels. That is something that we cannot prove, since we weren't there and weren't allowed to record due to privacy restraints and everything. But that is definitely something to keep in mind for the next, if there's a next iteration of this paper.
Thank you so much. So if there are no any further questions to Niels, again, if you have questions, write it into the Discord channel, and especially for the third presentation, Mike Wong, we will pass these questions to him, and we'll try to answer in the chat these questions as soon as possible. Thank you so much for all the presenters for these great presentations in the first session. We will now have a short break, and we will continue at local time. I'll guess in will be 9:50. Yeah, thank you for joining. See you after the break here again. Thank you.
Good morning, everyone. I hope you can hear me. Hello? Can anyone hear me?
Yes.
Hey, yes, I can hear you.
Hi.
Hello, Vladimir.
Good morning. Yeah, my name is Vladimir Todorovic. I'm signing in from Australia, from Perth. It's quite early in the morning here. So welcome to this session. Really excited to hear all these amazing papers. I would like to also just check if Nea Erlich is here. She's going to be the first one presenting. See, I don't think I see. So Nea Erlich, who is doing the first paper, virtual veracity. Nea, are you there? No, Nea is not here. Maybe we should wait for like a few minutes just to see if Nea will sign in. This is so yeah. Let me just I'll mute myself and then let's wait for 2 minutes and then we'll start. Yeah. So it looks like Nea is still not online, so maybe you're gonna have to wait for a few more minutes. I just emailed her, so let's just wait until Nea signs in, and in case she doesn't, in about a few minutes, we're supposed to start. What time is it now? 5 o'clock in Perth and 9 o'clock in New Zealand. So in case she doesn't show up before 9, we're gonna probably proceed with the second speaker. So let's just wait for a few more minutes, please. Sorry about this. Okay, good morning everyone again. So Nea doesn't seem to be logging in. Maybe she's having some issues to log in. So I think we're going to proceed with the second presentation. Second presentation is going to be a recorded video. So during the presentation, I'll turn off my camera, and please, if you have any questions for this presenter, please just upload them to our Discord channel or just post them on Zoom. That would be also useful. So we're gonna email the presenter all these questions and then post the responses back. So the paper is, first I didn't introduce myself too much. So my name is Vladimir Todorovic and I teach fine arts, animation and film at the University of Western Australia in Perth, in Wajak land. I also work in the field of animation and also VR. So yeah, that's me. So now we have a paper called a cardboard-based virtual reality study on self-avatar appearance and breathing. And this is a paper by Dixon Sui and Christos Mosas from Purdue University. So I'll play the video. I hope you can, yeah, maybe one more thing I need to do before I click sharing of the screen. I'm gonna, yeah, just share the screen. Again, I have to tick the sound box so that you can also hear the sound from this video. Okay, so just give me a second. So I'm gonna play this in case like you don't hear the sound or there's some technical glitches, please just shout, and I'm also gonna, yeah, stop my video for a sec.
Hello everyone and welcome to our presentation. I'm Milad Tusi. I'm an interactive media master student at the University of Applied Sciences Upper Austria.
Sorry, how is this not possible? This is not the correct one. My apologies, just give me a second. Just 1 second, sorry about this. Okay, so there it is. Sorry about this. So this is the presentation now.
All right, hello everyone. My name is Dishun. I am a PhD candidate at Purdue University. Today we're going to be presenting our research regarding our cardboard-based virtual reality study. This is a study specifically exploring our self-avatar appearance and also breathing. To start with a brief introduction, we decided to conduct this cardboard VR study because there are a lot of similar studies applied to other areas, and we wanted to use the cardboard VR application that we developed ourselves to answer the following research questions. So we wanted to find how different self-avatar, breathing motion assigned to the self-avatar, and also demographic factors such as prior VR experience and also age of the participants affect their sense of presence and also body ownership. And as for our related work section, we have found a lot of sources regarding studies about sense of presence, embodiment, and also cardboard head-mounted displays. So we know sense of embodiment, sense of presence, and also embodiment are important factors regarding virtual reality applications, just because sense of presence increases participants or VR users' felt experience, sense and sensibility, and also agency and autonomy within the virtual environment. While embodiment is also an important factor that describes the feeling of representing the avatar, it is important to have a strong sense of embodiment when they are in that immersive environment, whenever they have full controllability or part of controllability on their self-avatars. And we decided to use the cardboard head-mounted displays not only because it is widely applied in different areas, such as medical science, education, and also business, but also because of its low costness, and it's really applicable for most of the customers, comparing to the general customer level VR headsets such as Oculus Quest or HTC Vive, which cost about 10 times more than the cardboard HMDs. So as for our methodology, we recruited 80 participants from our department. We got 40 males and also 40 females. And as for the application, we have developed a Android VR application using Unity 3D, and we have got some of the cardboard from online, and we are using a Samsung Galaxy S9 phone with it to run this application and to set up with the cardboard VR. So as you can see, this is the avatars that we have used for our application. We are comparing realistic avatar versus mannequin avatar, and we have designed 2 different avatars for different genders. And also we have the breathing idle animation versus the non-breathing animation. So if there is the breathing animation applied on these characters, the character will show a really natural idle movement with like the breathing sound play in the application. The process is whenever the participant decided to participate into our study, we'll let them sign the consent form, finish up the demographics questionnaire, and then we'll let them we'll help them set up with the cardboard VR, and then we'll let them to sit in the same position as these avatars are sitting, and then we'll try to look at the environment for around 1 minute while also having the breathing pattern synchronize with these avatars as much as possible. And after the 1 minute experiment, they are required to answer the post questionnaire regarding presence and also body ownership. So as for the results, we have found significance on these different variables. So as for presence, we have found significance regarding different avatar. So it is showing that participants embodied in the realistic self-avatar reported significantly lower presence than those who embodied into the mannequin avatar. We have also found several significances on body ownership. So we got significant effect on interaction effect of age and avatar. So we're saying that younger participants experiencing the mannequin self-avatar reported higher body ownership illusion than the older participants. And we also found significance simply on age itself. That means younger participants on the younger participants who participated in the study, they reported higher body ownership than those of the older participants. We also found a 3-way interaction effect in between avatar, breathing, and also VR experience on body ownership. So from our post-hoc analysis, we're finding that participants with the prior VR experience reported higher body ownership illusion than those with no prior VR experience. And lastly, we also found an interaction effect in between breathing and also VR experience. Breathing over here refers to the animation of the self-avatar. And they're saying that participants with prior VR experience rated their body ownership illusion higher than when no breathing animation was assigned to the self-avatar than those with breathing motion. So from our previous results, we are here leading to discussion regarding these 2 different variables. First of all, on presence, we did find significances that it is indicating the higher sense of presence with a less realistic appearance, We believe this is something that is not aligning with the previous results, because we did find the previous VR study indicating that higher realistic appearance will actually lead to a higher sense of presence. In our case, we think the reason is that we are lacking the sense of agency, because there's really less motor control regarding the self-avatar. Basically what the participants are doing, they were just sitting on the chair and doing the minimal amount of movement. So this could be the reason for leading into a less realistic sense of presence. And as for body ownership, we found some significances regarding the breathing animation and also the prior experience and also the age. So we got younger participants rated higher body ownership with the mannequin avatar than the older participants. Of body ownership will actually decrease regarding their output results. And also, participants' prior VR experience will also lead to a more robust judgment and also body ownership. In this case, those participants who never experienced VR before, they will feel the mannequin style to be a really brand new, fresh experience for them, and they will lead to a higher body ownership than those who already experienced VR before, which will think the mannequin avatar to be less realistic in their opinion. So as for the limitation regarding the study, we have, first of all, limited hardware. We are running on a Samsung Galaxy S9, which leads to a really low frequency rate, frame rate. And there is a lack of eye tracking, and there's also limited adjustments of body height and size, since the application itself is pretty much fixed. There's also a need investigation on participants' previous computer gaming experience, so we have better understanding regarding their background. And lastly, there is a lack of motion using this type of devices. So as for a conclusion, we had avatar that had a great impact on presence and also age, significantly affected body ownership. These results can be essential design considerations for future cardboard-based VR applications. And as for the future, we want to import eye tracking, and also different motions can be applied to the self-avatars. And also we can compare in between high-end and also low-cost devices using the same type of experiment. So that will be it. Thank you guys so much for participating, and have a wonderful day.
Okay, so hope you can hear me. This is quite interesting. So just gonna wait to see if Nea is here. No, actually Nea is probably not here yet. And we have the final presenter, Hannes Roll, who is also not here. I guess like both of them are having issues logging in. So I'm gonna wait a little bit more just so that we don't stop the session. So let's wait for another 10-15 minutes. I'm gonna mute myself. If anyone has questions for Dikshan, please post them on Discord channel or here on Zoom, so we can get some replies from the authors. Yeah. Are there any comments or questions? So let's wait until like 10:30 to see how to proceed. I'm gonna mute myself. Thank you.